everybody. Thanks for being here. We'll give it just a few more seconds, make sure everybody's had a chance to join that wants to, and we'll get started. We've still got people connecting, so we'll give it just another minute. All right, well, welcome everyone. Thank you for being here today. We're glad to have you. We're in session 17 today. So if you've been with us since early summer last year, this is session 17. And today we're going to be focusing on calculating flow, detention time, and loading rates. So my name is Dawn Knoll, and I'm a project director with the Southwest EFC, and I will be leading the course today. And I have with me Valeria, and she will be helping to monitor the questions box, the chat box, make sure that things are going well for everyone. So if you're having any kind of technical difficulties, please reach out to Valeria and let her know, and she will give her best shot to help you. Zoom isn't always friendly in that way, but we'll give it our best shot to keep you connected and things moving forward. As always, we are a part of the Southwest Environmental Finance Center, which is a part of the University of New Mexico's School of Engineering. And this training series is funded by the Environmental Protection Agency. So thank you to the EPA for making all of this possible. If you haven't attended our previous 16 sessions and haven't been on Zoom, this is how you can control things with Zoom. You have a toolbar, possibly at the top of your screen, but more likely on the bottom if you're on a computer. So that control bar can disappear and pop up if you mouse over things. So take a look at that control bar, get familiar with it. Most importantly, the chat box or the mute button, the audio button. Since we are doing a math course today, I want to be able to give you the opportunity to unmute if you have a microphone and ask questions. If you don't have that capability, if you're in one of the group settings and you have a question, feel free to have someone chat that question in, and Valeria will help bring my attention to that. I want to make sure that we're answering your questions, that we're not leaving you more confused than when you walked in the door today. So please get familiar with that chat box and how to use it, and or how to unmute and ask questions. And everything else I think is fairly self-explanatory. So we'll be using that. We'll be using Zoom for the rest of the sessions throughout the course too. We are basing this series in a way that's used to supplement and reinforce the ABC need to know criteria for the wastewater operator level 1 and 2 exams. There will be some higher level topics covered, not today, but throughout the course. We won't always follow that exact order of the need to knows, but everything that we're doing is based on those. And so if you're not familiar with those or that website, please take some time to get familiar with it. Look at those need to knows. That's what your tests are based on. That's also where you can find the formula sheet that we'll be using and talking about today. So that website is gowpi.org. And then from there, the services and the ABC testing. So you can get to that site pretty easily and find those need to knows. All of the information that we're covering and more is in the guidebooks that you see here, the study books. And these happen to be our copy, so we use them all the time. You can see the Post-its. We encourage you to do the same thing. I think everyone should have access to these books through your utility. And if you don't, let me know. We can make sure that we help you to be able to access those resources. So our schedule for 2026, like I said, we've been doing this for over 6 months now. So 26 sessions in total. Each session is 1 hour. And this is the schedule for the remainder of this year. So we're currently in session 17, and you can see that we will go all the way through July of 2026 before we have touched on all of the topics that we want to make sure you guys are familiar with. So if you aren't able to attend any of the sessions, or you missed one, or you are just now becoming aware of them, we do have a website that has all of the sessions being posted so that you can go back and review them. You can re-watch the video, so the recording of the webinar is available. Also, just the PowerPoint slides are available. So you can download the video recording and the PowerPoint slides, whatever works best for you. So those are available at the website that you can see at the top of the page. So make sure that you're familiar with that page and you have access to it so you can catch up on anything you've missed. Also, a reminder to sign in if you're attending in a group so that we can keep track of your attendance hours so that you get your continuing education credits for your operator certification. So with all of that, let's get into today's content. I'm going to actually turn my video off so it's not distracting. But I am still here. If you need anything or have any questions, please make sure that you unmute or use that chat box. So today we're going to be talking about, like I said, some flow rate and some detention time math. So we're going to get started by discussing formulas that you would use to calculate velocity, flow rate, detention time, and loading rates. And throughout the session, we're going to have opportunities for you to do some practice problems, and then we'll walk you through the solution so you can see if you're fully understanding, or if you missed a step, or if you got the right answer or not. And if not, why not? So I would encourage you to grab a pencil and paper if you have access to it in the room that you're in. And also the ABC formula sheet would be helpful. When you're taking the test, you're going to use that sheet and you're going to refer to it a lot. So we just want you to, get familiar with it, see it. So I do have the website on the bottom of the screen here, but also Valeria is going to put the sheet in the chat. So if you're on your own computer, you can click on it and download it straight from there. It is a PDF. If you use the web address that's on the screen, it will take you to their website, and then about halfway down is the wastewater formula sheet that as soon as you click the link, it downloads to your computer. So if you have access to that ABC formula sheet, it would, could be helpful today. If not, make sure that you get access to it, you become familiar with it, you understand what the formulas are and where they are, because being familiar with that sheet will save you so much time when it's time to, come time to take your test. So I want to make sure that you're familiar with it, you have access to it. And for anyone that doesn't get it right now, Valeria will share it again before the very first practice problem. So we make sure everyone's got ample opportunity to see that sheet. So let's go ahead and dig right into velocity and flow rates. So when we're talking about velocity and flow rates, sometimes we can confuse them or think that they're the same thing, but really they're two different things with similar components. So velocity is talking about how fast, and flow rates are talking about how much. Or if you can think about it kind of like speed and volume. So those are the two numbers that we're going to start with, formulas we're going to start with. So velocity and flow rate. How are they similar and how are they different? Well, velocity is talking about how fast the water flows through a pipe in a given amount of time. So how far something travels in a given amount of time. So feet per second, meters per second. That's a speed, right? Miles per hour. That's the same type of concept as feet per second. So that's the velocity units are feet per second, meters per second, miles per hour, although we don't usually measure water flow in miles per hour. So those are velocity terms. And then with flow rate, this is the volume of water flowing through the pipe in a given time. So how much, not how fast, but how much water is going through that pipe. So this would be gallons per minute or cubic feet per second or millions of gallons per day. So all of those things should be terms that you've heard and that you understand, and just keeping the difference in your head and knowing velocity is speed or how fast, and flow is how much or volume, right? So understanding those differences is important because you use those terms a lot, and confusing them can make things pretty challenging. So just keep in mind the differences here. And then if you think about it, velocity in feet per second, well, to get that, there's a couple of calculations that you can use. So you can use flow rate, which we're talking about here also, divided by the area of the pipe. That gives you feet per second. Or you can use distance divided by time. So that would be feet per second, feet per second. And then flow rate, to calculate flow rate, you're going to take the area of the pipe and multiply it by the velocity. So you can see here, flow rate is in the velocity calculation and velocity is in the flow rate calculation. So they're obviously related, but they're not the same thing. They don't have the same units. They're measuring two different things. So we want to make sure that you're familiar and you understand those two terms and those two concepts. So down here in the green box, velocity, feet per second, flow, cubic feet per second, or gallons per minute. And of course, the difference between gallons per minute and cubic feet per second is just that the units are different. So we can always convert from cubic feet to gallons. And of course, you can convert from seconds to minutes to hours. You guys know how to do time conversions, straight out of grade school. So those unit conversions make sense to us because we have to do it all the time. But going from cubic feet to gallons sometimes feels a little bit foreign to us. So understanding that these are the same types of units, gallons per minute, cubic feet per second, millions of gallons per day. They're just measuring larger or smaller kind of concepts or units. So keeping that green box in mind is important, and understanding those differences is something we really want to make sure that you understand and can do. So first, we're going to take a look at a velocity calculation. So this example is kind of fun. The picture is a huge rubber duck, but in our example, the rubber duck fits into your pipe. So this is how you can measure velocity. You can put something into the beginning of your pipe and see how long it takes for it to come out the end and how long is the pipe, and you'll know your velocity. So the velocity calculation that we're going to look at is you put a rubber ducky at the beginning of a pipe that is 520 feet long. It comes out the end in 142 seconds. How fast is water flowing through your pipe? And we do assume that water is flowing at the same speed as the duck, that there's not some baffling or something weird happening in the pipe, or that the duck's just going through a straight pipe flowing at the same speed as the water. So we know the velocity calculations. We can find those on our sheet, and we have these two options. Velocity is flow rate divided by area, or velocity is distance divided by time. And so if we look, we have a length and we have a time. So it looks like we're probably going to use that second equation, distance over time. So if we use distance over time, we put the 520 feet in for the distance and the 142 seconds for the time. And we do that math with a handy calculator, which all of us have in our pockets these days, in our phones. So we can do that math quickly, and we come up with 3.7 feet per second. So if we look at our answer sheet, we've got A, B, C, D, and 3.7 feet per second matches the D choice. So D would be the answer that we choose. So that's a quick velocity calculation, distance over time. All right, so let's go back to that velocity versus flow rate. So velocity is speed, flow is volume. So now let's take a look at a volume calculation. So if we're looking at flow or volume, you are going to be measuring things slightly different. So your flow meter is for your lift station pump's broken, but you want to figure out the pump's capacity. So you open up a valve and fill up a 5-gallon bucket, and you fill up 8 buckets in 1 minute. So what's the capacity of your pump in gallons per minute? So this is just a simple way to think about flow, right? How much water is moving through that pump or that pipe? That's flow, right? So in this case, we've got 8 buckets in 1 minute, and we know that flow is volume over time. So if we have a 5-gallon bucket and we have 8 buckets in the 1 minute, we can do that math, 5 times 8, and our units cancel from the bottom to the top. That's how we do our unit conversions, right? The bottom always has to cancel the top. It can't be top canceling top, or we get buckets per buckets or gallons or not the units we want, right? So we want to get gallons per minute. So we know that those units are canceling. So 5 times 8 is 40 gallons per minute. So we look at our answer sheet, and lo and behold, there it is, answer B. So that's a concept of flow, but this is probably not the type of question you're going to see on an exam. But we want to share this with you because this is really what flow is all about. How much water in how much time, right? So here's a question that you're more likely to see on an exam. What is the flow in gallons per minute in an 18-inch diameter line when your rubber ducky is moving through it at a velocity of 2.5 feet per second? The test probably won't talk about your rubber ducky, but it will probably give you the velocity. So what do we know, and what are we trying to get? Well, we know that we've got velocity of 2.5 feet per second. As you can see on this picture, that duck's moving at 2.5 feet per second through an 18-inch diameter pipe. So we also know that diameter is 18 inches, so we can convert that to feet. So we divide by 12 to go from inches to feet. So that's 1.5 feet. And we know the radius is half of that number, right? The radius is half of the diameter. So the radius here is 1.5 divided by 2, or times 50%, or however you like to do halves. But that's 0.75 feet. So now we know the velocity and we know the radius of the pipe. We also know from our equation sheet that flow rate, which is what this question is asking, right? What is the flow? So we look for the flow equation, and we know that it's area times velocity. So we know velocity, but do we know area? Well, not really. We know diameter, we know radius. So we go and look, and sure enough, the area of a circle is pi times r squared, or 3.14 times the radius. And so we can calculate the area of the circle. We have the velocity of the duck, so that means we can get to the answer. So let's take a look at how this math goes. So if flow is velocity times area, and area is 3.14 or pi times r squared, we're going to look at 3.14 times 0.75 feet squared, which is 3.14 times 0.75 times 0.75. And that gets us to 1.77 square feet. Okay, so now we've got the area. So let's go back to our flow calculation. We've got the velocity is a given, 2.5 feet per second times 1.77 feet squared. And the first thing we want to do here is make sure we don't have inches and feet. We don't have miles and feet. We've got feet and feet. That means we are allowed to do that math without any unit conversion. So we've got feet and feet. So we're good to do that math. So we know the flow is 4.42 cubic feet per second. Phew, great, got it. Oh, wait. What units did they want the answer in? Not cubic feet per second, but gallons per minute. So now we do need to do some unit conversion, right? So 4.42 cubic feet per second to get to gallons per minute, we're going to need to look at our conversion factors. So how many gallons is in 1 cubic foot? Well, we see on the conversion sheet, 7.48 gallons is 1 cubic foot. And how many seconds is in 1 minute? We know 60 seconds in 1 minute. So now we can get from cubic feet per second to gallons per minute just by multiplying out those numbers. So that's going to look like this. We take our answer, the 4.42 cubic feet per second, and we want to put our units in the right order. So we want to have cubic feet on the bottom and we want to have seconds on the top. So we're going to put 1 cubic foot on the bottom and 7.48 gallons on the top. And then 60 seconds on the top and 1 minute on the bottom. And now we can multiply across after we make sure our units cancel. So cubic feet cancels out, seconds cancel out, and that leaves us with gallons per minute, which is what we want. So 4.42 times 7.48 times 60 equals 1,984 gallons per minute. So that's how we do a flow calculation with unit conversion. So we really had to do several steps there, right? We had the equation and we knew the velocity, but we didn't know the area. So we had to calculate the area. Then we got the answer, but not in the correct units. So we had to do unit conversion. So that's what some of those test questions can look like. You've got to make sure that you understand what you're given and what you're looking for and what's it going to take to get from what you're given to what you're looking for. Because if you stop here, 4.42, that's not going to be one of the choices more than likely. Or if it is, it's still going to be the wrong answer because it wasn't in gallons per minute. So now it's your turn to try it. Valeria's put that equation sheet in the chat box again. If you don't have it, try and get it downloaded, try and take a look at it. But this is a similar question to what I just walked you through. So get out your pen, get out your pencil, your paper, and we'll let you guys have some time to work on this. And then I will jump back on. So what is the flow in gallons per minute in a 12-inch diameter line when your rubber ducky is moving at a velocity of 1.1 feet per second? So your turn to try it, guys, and I'll give you a couple minutes, and then I'll walk through the answer and see how it went. For the chat that just came in, if there was a poll question, there isn't. We're going to walk through the solution together. So if you're working on it on paper, you can see, the steps you took and the steps that it would take to get there and make sure that you could do it. You did it all right. No problem. All right, so let's get started walking through this together. So the first thing that we did last time was, what do we know? And what are we looking for, right? So what do we know? We know the diameter of the pipe is 12 inches, and we know the velocity is 1.1 feet per second. So I drew out a nice little picture so I know what's going on here. And then I'm gonna do a little bit of quick math. If I know the diameter of the pipe, I know I'm probably gonna need to get units in feet, because I've got inches and I've got feet in the givens. So I'm gonna go ahead and do some conversion to feet, right? So the first thing I do is the diameter is 12 inches. So we know 12 inches is 1 foot, and then half of that's the radius. So it's a half a foot radius. And that's going to help us to do what? That's going to help us to calculate area, because we look and we say, okay, we've got to calculate flow. What's the flow equation? It's area times velocity. I know velocity, and I can calculate area. So that's our next step. Next, we're going to calculate area. So we know area is pi r squared. And so pi is rounded to be 3.14 times the radius times the radius. That's what the squared means, right? R times R. So we do that math. 3.14 times 0.5 times 0.5 gives us 0.785 square feet. So now we know velocity and we know area. So we can use the formula that gets us to the flow answer that we're looking for, right? So velocity times area, 1.1 feet per second, times the 0.85 square feet that we calculated for area. And that gives us 0.864 cubic feet per second. Once again, right? Got the answer. Except that's not the answer. There's none of these look the same. Why is that? That's the units. So we've got to take a look at the units and do some unit conversions. So we're going to look at our conversion factors, 7.48 gallons in a cubic foot and 60 seconds in a minute. And we're going to use those to do that exact same conversion. So we take our answer and we write it out in the grid. We put our conversions in there. We cancel out all of the units that we can. So cubic feet and seconds, leaving us gallons per minute. Now we can multiply the 0.864 times 7.48 times 60. And you guys, just to make sure we're clear, if any of these numbers down here were not 1, we would multiply the top, we would multiply the bottom, and we would divide the top by the bottom. But since the bottom is 1 times 1 times 1, we don't have to divide, because any number divided by 1 is the same answer. So that's why I'm saying just multiply the top, but always take a look at your bottom too and make sure if there's any numbers down here that aren't 1, that you do that division as well. So doing that math, 0.864 times 7.48 times 60, we get 388 gallons per minute. And lo and behold, that is the answer A on our sheet. So any questions there? Did anybody run into any issues there that you want me to review or talk about before we move on? Feel free to type it in the chat, or if you can unmute, feel free to do that as well. All right, so I'm not seeing or hearing anything right now, but if there are questions and we need to jump back, feel free. Like I said, I want to make sure I don't leave you more confused than when you entered the room today. That is not my goal. So I want to make sure we answer any and all questions. All right, so we're going to move in to the next type of kind of flow rate question. This time we're going to be looking at detention time. So we understand velocity is speed. We understand flow is volume. And now we're going to use those to understand some wastewater questions. So detention time. So when we're looking at detention time, we want to think about how, the different applications and where we might encounter this in real life, not just on the test, but where might this come up in your day-to-day work. So when we're talking about detention time, this is the time that water stays in a reservoir or a treatment process or a tank or any kind of structure that water is entering and is held for some time while it's kind of moving through that structure before it exits. So detention time helps us with understanding lots of different things. And so when you're calculating detention time, you're using it to understand how long the water is being exposed to something or being allowed to settle, or just different applications of how long that water is in that space. And you can see it could be detention time for the picture on the left of one type of tank, Or detention time for a picture on the right, where it's going through several different phases and processes. So you would be calculating volumes of different chambers or different places where the water goes and adding it all together at the end. So it could be a single chamber, it could be multiple chambers. But what's important to know is that detention time is volume over flow, right? And so we just looked at flow and we know what volume is. That's how much water is in that tank versus how fast that water's, not how fast, I said that wrong, how much water is going through that tank. And that gives you the time. And so we always want to note that no matter what you're doing, your units have to be compatible. You cannot have, cubic feet and gallons. You cannot have minutes and seconds. You have to have the same thing all the way through all of the math. And that can be the trickiest part of some of these questions is the units. So we want to, I will say it probably more than 5 more times today. I don't know. Maybe if you guys had a bingo card, you could count and see. But units have to match. They have to be compatible. So let's take a look at a detention time example. So your secondary clarifier is 40 feet in diameter and 25 feet deep. Your max daily flow is 1.2 million gallons per day. To determine if your clarifier meets the recommended detention time, you need to calculate the detention time of the clarifier in hours. So drawing a little sketch can be really helpful, can help you visualize, think about what's going on. So we have a little sketch that says it's 40 feet in diameter and it's 25 feet deep. And we also know that the radius is half of the diameter, so we can put that on there too as 20 feet. So that's a starting point. That's what we know. They tell us that it's 40 feet in diameter and 25 feet deep. We also know the flow rate, right? So it says the flow is 1.2 million gallons per day. So right there, we have feet and we have gallons. So we know that the units don't match. But the first thing we need to do is figure out what formula we're going to use. So we need to calculate the detention time, it says. So detention time calculation, here's the formula. Detention time is volume over flow. So what do we know? Do we know volume? Not really. Do we know flow? Yes, we know that it's 1.2 million gallons per day. But can we figure out the volume? We can, because we know the size of the tank. So that means we can figure out the volume. So now we look for a volume equation, and we know that volume of a cylinder is pi times r squared times the height of the tank. So do we have everything we need? Pi is a number, 3.14, r squared. Well, we calculated the radius, so we've got that. Height, yep, they told us how deep it is. That's the height. So we can calculate the volume. So if we start there, volume is 3.14 times 20 times 20 times 25. And that comes out to be 31,400 cubic feet. Okay, so now we've got volume in cubic feet, and we've got flow in millions of gallons per day. So we've got unit issues. So we've got to convert one of the units. So let's go ahead and convert the cubic feet into gallons. So we look for the conversion unit, or the conversion factor, and 1 cubic foot is 7.48 gallons. So we can do this math, cancel out the units, top and bottom, and we get 234,872 gallons. Okay, so now we have volume in gallons, and we have flow in millions of gallons. But we can do that math too, because going from gallons to millions of gallons is also a conversion factor. So if we take our volume and we put it over our flow, and we convert millions of gallons to gallons, that means 1 million gallons is, lo and behold, 1 million gallons. And then we have our hours to days calculation, conversion, right? So now we can cancel out those units. And I just want to point out that D in the MGD is per day, right? So that's the day unit that we can cancel out. So now we're down to hours, and that's what it's asking for, the detention time in hours. So we do that math, we get 4.7 hours, and that's one of the choices on our list. So we've got this pretty simple equation, volume over flow, but we didn't know volume. We knew diameter and we knew depth. Those are very realistic things, right? You probably have places where you're not certain of the volume of a tank, but you do know its diameter and you do know its depth. So you can calculate the volume. So this is just a practical kind of example of understanding some of the steps you have to take to be able to do the math that they're asking for. So it says that we needed to calculate the detention time. Why? Because we wanted to determine if our clarifier meets the recommended detention time. So the recommended detention time is greater than 2 to 3 hours. Did we succeed? Is our clarifier sized appropriately? Well, at this flow rate, the answer is yes. We're doing all right with detention time. So that's a practical application, but could also be very likely be on a test, right? So one example there. So if we go to an example problem here, this one is the harder one. This one is where you've got multiple tanks, multiple sizes, and a flow rate. And so you just have to work through this one tank at a time. So just take it one step at a time. It's very much the same problem. It just takes a little bit longer to get there. And you might see something like this. So this is saying, find the detention time in hours for the following wastewater treatment plant. The plant has 4 rectangular clarifiers that are each 40 feet long, 30 feet wide, and an average water depth of 21 feet. And 1 oxidation ditch that's 295 feet long, 80 feet wide, and with a water depth of 11 feet. The flow is 3.5 million gallons per day. So just like before, we have feet, we have gallons. So we know that there's going to be some unit conversions. We know that there's going to be some calculations, probably of volume, because we've looked and we know that the equation for detention time is volume over flow, and they haven't given us volume. And when I say over, I don't mean overflow. I mean divided by. This tank's not overflowing. It's volume divided by flow. So we know that we're going to have to calculate the volume for each of these tanks, and then we're going to have to do some unit conversion. So what are we going to start with? Let's start with volume. So to calculate volume of a rectangular tank, we look at the equation sheet and we find that volume of a rectangular tank is length times width times height. So let's start there, right? We've got 4 clarifiers that are 40 feet by 30 feet by 21 feet. So we can do that math quickly and we get 25,200 cubic feet. That's 1 clarifier, right? So now we have to multiply that. Oh, I'm getting ahead of myself. We're going to go ahead and convert the units. We're going to go ahead and make these gallons. So we've got 25,200 cubic feet. And then we go ahead and put the unit conversion in there from cubic feet to gallons. We can cancel out the units that match. And that says we've got 188,496 gallons. And again, that's 1 clarifier. So 4 clarifiers, we multiply that 1 times 4 to get 753,984 gallons. Okay, so now we're done with the rectangular clarifiers, but we have the oxidation ditch remaining. So next we're going to take a look at the oxidation ditch. So we know that we've got the length, the width, and the depth. So we know we're going to use that same volume equation and come up with the cubic feet. And then we're going to do the unit conversions. We cancel out the units that match and get our answer of 1,942,000 gallons. So now we know the volume of the 4 clarifiers plus the volume of the oxidation ditch. So we can add those together and get our total volume of the wastewater treatment plant. So now we have volume, it's in gallons, but our flow is in millions of gallons, right? So we can do that conversion where we take 2,695,984 gallons divided by 1 million gallons to get 2.65984 million gallons. So now we have everything we need. The units match, so we can go back to the equation that we were looking at the beginning. Detention time is volume over flow. Are our units compatible? Million gallons? Yes, they're compatible. So we can do the math of 2.7 divided by 3.5, and that gives us 0.77 days. Do we have the answer? Not quite, because it asked us for detention time in hours. So one more conversion. We go from days to hours. Again, canceling the units that we can. That's 18.5 hours. So that's the detention time for that entire wastewater treatment plant. So that feels like a lot. It took what, 4 slides full of math to get to the answer. But really what we did was calculate the volume of the rectangles, the clarifiers, the volume of the rectangular oxidation ditch, converted units, and use the equation that was given. So don't get overwhelmed when you see questions like this. Slow down, take a breath, think about what it's asking, and do you have everything you need to be able to do this math? And if so, you can get to the answer. This one takes a little longer, so you might want to circle the number and come back to it if you have time. Things like that, because when you see, I'm going to have to do, 4 steps to get to the answer. I'm going to have to, this is going to take more than 1 step. Maybe I want to come back to this one. But this one's not a super hard one. It's just thinking through what the steps are. So, when you circle it, you might want to mark that it's just long, but that you can do, the formulas, you understand the math. So I don't want to scare you by putting something like this out there. I want to encourage you to think about, when does it make sense on the test to do a longer problem, and when does it make sense to skip it and come back? So when you read this question and you have to quickly make an assessment, you can say, well, okay, I've got to do volume time of the clarifiers, volumes of the oxidation ditch. I've got to do some unit conversions because there's feet in here and gallons in here, and there's days and there's hours. So this one might take me a little longer, right? So this is something that you might think you're capable of doing, but it's going to take a fair amount of time. So let's see if there's time at the end of the test to come back to this one and get to the ones that you can do faster. But this type of question is very realistic. This is something you might need to do for your job, where you're not under a time crunch to get the test done and the time limit. But this is where it could become very practical in understanding detention time and how long that water's sitting in your plant before it actually comes out the other end and being treated. So this might be something that's way more practical, and understanding it for practical reasons is probably more valuable than understanding it for the test. So don't let this type of question scare you. Just think it through and think about, when is the best time to attack it. Okay. So 18.5 hours is the detention time for the entire treatment plant and the wastewater treatment plant. This next one is a rearranging equation. So we have detention time and we're asked for something different. So a circular clarifier is being designed to accommodate an average flow of 76,250 gallons per day. To accommodate the space restrictions of the plant, I know you guys encounter this, where there's not a lot of room for something new to be added. So there's space restrictions. To accommodate the space restrictions of the plant, the diameter of the clarifier must not exceed 13 feet. So that's as big as round as it can be, but it can be as deep as we want it to be, right? So what must the designed depth be to achieve a detention time of 2.5 hours? So if you're looking for an equation that is depth equals, you're probably not going to find it. But if you look for an equation that's detention time, you're going to find it. But that means you're going to have to rearrange the formula. So this is something that comes up, more often than not. So the detention time equation, detention time is equal to volume over flow. Q is flow. I know that's weird. But F is used for other things all over the world for various reasons. So Q is flow. So detention time equals volume over flow. And we know detention time, and we know flow, and we're looking for depth. So that means we need to use the volume to get to depth. So we're going to rearrange the equation. So that means we want volume to be on one side of the equal sign and everything else to be on the other. So to do that, we have to get Q from this side of the equation to this side of the equation. So since this is a division, that means we multiply both sides by Q and cancel Q out on one side and move it to the other. So volume equals detention time times flow. So detention time times flow, well, we've got all of that information, and we just need to do 1 unit conversion for time and 1 unit conversion for volume. So we can put all of that in here and get it all done in one fell swoop. So we've got detention time, Q, 2.5 hours. We're going to convert those hours to days. So we go ahead and put that unit conversion in there. And then we've got flow. So we've got 76,250 gallons per day. And again, we're trying to get to a depth in feet, right? So we're going to convert gallons to cubic feet so that we can get there. So we have those conversions. We do the math, multiply across, and you can see this one has numbers in the top and numbers in the bottom. So this one we have to multiply 2.5 times 76,250. And we have to multiply 24 by 7.48. And then we divide the top number by the bottom number. So that comes out to 1,062 cubic feet. Okay. So that's your volume. Is that the depth? No. But do we know how volume and depth are related? We do, right? We know volume of a circular clarifier is pi r squared times h. And we're trying to get h. So that means, again, we're going to have to rearrange the equation. So h, we want h to be on one side by itself and everything else to be on the other. This is multiplication, so that means we have to divide both sides to cancel this out. So h is equal to volume divided by pi r squared. So we take our volume that we calculated just above, and we divide it by pi times r squared. And making sure the units feet and feet, yep, we can do that math. We don't have to do any unit conversions. So that says our height is equal to 8 feet. So is that the answer that we're looking for? Let's double check. The design depth to be able to achieve a detention time of 2 hours, it must not exceed 13 feet. Are we good? We're good. So we know the depth is 8 feet. It doesn't exceed 13. We know we get the 2.5 hour detention time with the flow that's predicted, right? The average flow that's predicted. So this is the same type of math, detention time, but you're rearranging equations. Okay? So I'm going to give you guys a few minutes to practice the detention time problem. And then we've got one more concept after this and we'll be all done. And I know it's a lot for a brain in 1 hour to take all this in. So, so make sure you're reviewing this. Make sure you're asking questions. So here's your turn. Here's your practice question. You've got a rectangular sedimentation basin that's 75 feet long, 30 feet wide, and 20 feet deep. If the treatment plant has a daily flow rate of 2.25 million gallons per day, what is the detention time in hours? So I'm going to give you a couple minutes and check back in. All right, so that was a couple of minutes. So goes by quick when you're doing the math. So we're going to start by looking at what is it that we know. So we know the dimensions. We know it's 75 foot long by 30 feet wide by 20 feet deep. And we know the flow rate, 2.25 million gallons per day. And what are we looking for? We're looking for the detention time in hours. That's what they're asking us for, right? So what are we going to need to get there? Well, we know we're going to need a detention time equation. So detention time is volume over flow. And we know that we don't have volume, but we do have flow. So we need a volume equation. Volume is length times width times depth. And we know we've got feet and we know we've got gallons. So we're going to have a conversion factor of cubic feet to gallons. So we've got all of the things that we need now to figure out the answer. So if we first calculate the volume of the basin, we take the length times the width times the depth, because that's the first thing we've got to figure out is volume. We've got 75 by 30 by 20. Multiply those together, that's 45,000 cubic feet. So we know we're going to have to take those cubic feet to gallons. So we're going to do that conversion, 45,000 cubic feet times 7.48 gallons per cubic foot. That gives us 336,600 gallons. So now we've got volume. So we can use the detention time calculation. Detention time is volume over flow. We've got the volume and we've got the flow. The flow was given to us in millions of gallons per day. So we multiply that by a million to get the 2,250,000 gallons. And we do that math and we get 0.1496 days. So are we at the answer? Not just yet, right? Because we have days and it asks us for hours. So we are going to convert our days to hours. So we use that conversion factor. 1 day is 24 hours. So we multiply the 0.1496 times 24 to get 3.6 hours. So those were the steps that you needed, 4 steps to get to your answer. But first you had to figure out what you needed to get there. What equations did you have? What were you given? So when you go through this process of what do we know? What are we looking for? And what do we need to get there? You can do these equations, you can do this math and figure out kind of the order that you're going to do them in and the steps that you're going to take. So any questions on this example? All right, so our last concept for today is one more type of calculation where we're looking at flow, but we're looking at a slightly different idea. So here is the weir loading rate. This measures the amount of water that's leaving a tank per linear unit of the length of the weir. So this is used for a variety of reasons to make sure you're not hydraulically overloading the weir, that you have efficient sedimentation occurring, solids aren't infiltrating the clarifier effluent. So there are recommendations out there about what weir loading should be, 10,000 to 20,000 gallons per day per foot. And this typically correlates with your correct detention time. So what we were just talking about with detention time, if your detention time is not long enough, your weir loading rate's probably not going to be right. You're probably going to see issues with solids coming over the weir, solids not settling, things like that. So weir loading rate, or the weir overflow rate, depending on how it's worded, is your flow rate over your weir length. So instead of it being flow over volume or volume over flow, it's volume or flow over length. So similar math, similar units, but telling you a slightly different piece of information. So here, if you see the word weir, that's a pretty good indicator that weir length is involved, and that's the equation you need to use, right? So if we look at an example, weir loading rate, the flow for a circular clarifier is 1.2 million gallons per day with a 26-foot diameter. What is the weir overflow rate in gallons per foot of weir length per day? So we know we've got the equation. Weir length is a line, but we have a clarifier that's round. So we have to figure out the circumference, the length all the way around the outside of that clarifier. So it's almost like we're going to take that clarifier and and we're gonna turn it from a circle and we're gonna stretch it out and make it a straight line. So length of a clarifier is the same as the circumference of the circle, which is pi times d. So we've got the flow rate, and we've got the length, and we've got gallons per day per foot. And that's what it asked for in the question, gallons per foot, right? So we're gonna do the math, 1.2 million or 1,200,000 gallons per day divided by 26 times pi. So 1,200,000 divided by 81.68. I was supposed to be clicking those while I was talking, obviously. I failed to do that, sorry. Those are the things that we need to calculate to do the math that's below. Have them out of order. So we've got our volume, or we've got our length, we've got our volume, our flow rate. Sorry, we have all discombobulated now. We've got our flow rate, we've got our length, we do the math, and we get the answer, 14,691 gallons per day per foot. So we're going to round that approximately 14,700 gallons per day per foot. So for the sake of time, I will let you guys do these practice questions on your own, and you can see how they go. But the answers will be in the slides whenever you get them. So it walks through one at a time, and you can look at those. The next topic is surface loading rate. And so this measures the amount of water passing over a unit of a surface area per day. So this is another parameter that indicates your clarifiers are not hydraulically overloaded. It has another direct relationship to your settlable solids and your removal efficiency of your sedimentation tanks. And again, there's some, design recommendations that you can use to see if you're operating in the right ranges. So the surface loading rate equation is flow, same as last time, flow rate divided by, but instead of length, it's divided by area. So again, we're looking at something slightly different to help us understand how our plant's operating, if things are staying in the tank long enough. So if we look at surface loading rate, again, this is where you're going to see the word surface and use it as an indicator that you should look for that surface loading rate equation. Uh-oh, Renee. She just put some crazy faces in the comments. So each one of these formulas, right, is on your equation sheet. So knowing the words and understanding what they're asking for helps you pick the right equation. So whether you're dividing by length, or you're dividing by volume, or you're dividing by area, they're all very similar. So looking to find the right equation is super important. And that's why I said at the beginning, understanding that equation sheet and knowing where to look for equations helps you out so much on the actual test. So I really encourage you to get familiar with that equation sheet and understand, if I'm looking for the word surface, where am I going to find it? If I'm looking for the word weir, where am I going to find it? So those are the indicators, right? The words help you find the right equation. So this is another example where they give you a circular clarifier with a depth of 8 feet, a diameter of 9 feet, and effluent flow of 42,000 gallons per day. And they want to know the surface loading rate. So we know the surface loading rate equation is flow over surface area. Surface area, well, we're looking at a circle. So we find the surface area of a circle, or the area of a circle, that's pi r squared. So now we've got Q, 42,000 gallons per day, which they give us, divided by the surface area, which is the pi times r squared. So r, well, we've got the diameter is 9, so we know that the radius is 4.5. 4.5 times 4.5. That gives us our equation at the bottom. And I think that I have things out of order again. I apologize for the backwardsness there. But pi times 4.5 feet times 4.5 feet gives us the answer in the bottom, the 63.6 feet squared. And we can divide 42,000 by 63.6 to get our answer of 660 gallons per day per square foot. Okay. Here we can do some unit conversion and, oh, nope, I lied completely. Here we don't need to do any unit conversion. We've got the answer in gallons per day per square foot, and that's a perfectly acceptable unit. You would see this in your answer sheet. So you're good to go here. I have another practice problem, and again, for the sake of time, we're past time already. I will leave it for you guys to practice on your own. If you have any questions about how these work, or you're not getting the answer, or things don't make sense, please reach out to us. We're happy to help you on a one-on-one basis to work through more of these problems with you, whatever we can do to help you get there. So these are all flow, volume, area type questions. The biggest thing to understand here is really your units and finding the equation that you need to get to the answer. So hopefully this has been helpful today and not super intimidating, but we are here to always go through and help you with any questions you have. So before we close out today, I know we're a couple minutes past time, but if you have any questions that you'd like to ask me now, I'll stick around for a few minutes and we can try and tackle those. Otherwise, thank you for being here. Here's our general contact information. I think most of you have my email address, though. It's my first initial D, last name Null @theunm.edu. So you can reach out to me directly too if you want to. So thank you all again so much. And like I said, I'll stick around in case anybody's got any questions. Yeah, Stephen, we can put the website in the chat. Give me just a second. I think I still have it pulled up. No, but I can pull it up here real quick. All right, I just put the link to the website with all of the recordings in the chat, and hopefully you can just click it and go straight there. But if not, let me know so we can make sure we get you there. All right, guys, thank you so much. Last chance for questions before we end the session. Thank you again. I hope you guys have a good rest of your day.